You probably think the speed of light is just a number. 299,792,458 meters per second. Fast. Incredibly fast. The fastest thing we've ever measured. Okay. But stop for a moment and ask a real question. Why that speed? Why is it the limit? Why can't anything go faster? What actually stops you? Most people never really ask this. They memorize the fact and move on. Einstein said so. The speed of light is the universe's speed limit. End of story. But that's not an explanation. That's just repeating a rule without understanding where it comes from. When you seriously dig into why nothing can outrun light, when you look at what's really standing in the way, you run into something deeply unsettling. Something that doesn't behave like anything in everyday life. Something that completely reshapes how space and time work. Because the speed of light isn't just a speed. It isn't simply the fastest thing around. It's part of the universe's blueprint. It's woven directly into the fabric of space and time themselves, so deeply that trying to go faster doesn't just fail, it stops making sense altogether. Let me show you what that means. We'll start simple. With something everyone understands. Objects fall. Drop an object, and it falls. Simple. Predictable. Galileo measured it centuries ago. In the very first second, an object falls about 16 feet. Doesn't matter what you drop, a ball, a stone, anything at all. 1 second passes, and it has fallen the same distance. Now think about the moon. The moon goes around the Earth. It isn't crashing down. It stays up there, tracing a circle in the sky. But here's the key question. Is the moon actually falling? Imagine the moon suddenly stopped moving sideways and just hovered in space. What would happen? It would fall straight toward Earth. Gravity would pull it in, just like it pulls everything else. But the moon isn't standing still. It's moving sideways, tangent to its path, at enormous speed. So while gravity pulls the moon inward, the moon keeps sliding sideways at the same time. It falls toward Earth and misses. Over and over again. That's what an orbit really is. Endless falling, combined with enough sideways motion to never hit the ground. And this is where Newton had his moment of brilliance. The moon sits about 240,000 miles from the center of the Earth. We, standing on the surface, are only about 4,000 miles from that same center. That means the moon is roughly 60 times farther away than we are. Newton asked a simple but powerful question. What if gravity weakens with distance? More precisely, what if it follows an inverse square law? That would mean this. Double the distance, and gravity becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. Increase the distance by a factor of n, and gravity weakens by n squared. So at the moon's distance, 60 times farther away, gravity should be 60 squared times weaker. That's 3,600 times weaker. Now look back at Earth. Here, an object falls about 16 feet in the first second. If gravity out at the moon is 3,600 times weaker, then something at that distance should fall toward Earth by 16 feet divided by 3,600. Do the math. That comes out to roughly 1/12 of an inch per second squared. Let me rephrase that, because this is the crucial part. According to the equations of motion, distance fallen grows with the square of time. So over 1 second, that tiny 1/12 of an inch is multiplied by 3,600 adds up to 16 feet. Exactly the same value we measure here on Earth. Perfect agreement. Newton calculated how far the moon should fall toward Earth in a single second, assuming gravity really did weaken with the inverse square of distance. And it matched. Perfectly. The moon was falling at exactly the rate Newton's law demanded. This was enormous. This wasn't a clever story or a loose explanation. It was a hard prediction that came true. Newton took one fact, how fast objects fall here on Earth, and tied it to something that seemed completely unrelated: the moon's distance and the timing of its orbit. Two separate observations. One single law. Once those pieces snapped together, there was no turning back. And Newton didn't stop there. He pushed the math further and asked another question. If gravity follows an inverse square law, what shape should planetary orbits have? The answer came straight out of the equations. Ellipses. And that's exactly what astronomers had already observed. Kepler had measured the shapes of planetary orbits with incredible accuracy, but he didn't know why they had that shape. Newton gave the reason. One law explained falling apples, the motion of the moon, and the paths of the planets. Three mysteries. One framework. Then even more pieces clicked into place. Take the tides. Why does the ocean rise and fall every day? Because the moon pulls on the Earth. But that raises a problem. If the moon simply pulls water toward itself, there should be only one high tide, on the side of Earth facing the moon. Yet we see two high tides roughly every 12 hours. Why? Some people thought the Earth was being pulled away from the water. Others thought the water was being pulled toward the moon. Both ideas pointed in the right direction, but neither told the whole story. Newton saw what was really happening. At the same distance, the moon pulls on the Earth and on the oceans with the same gravitational force. But the oceans aren't all at the same distance. Water on the side of Earth facing the moon is slightly closer, so it feels a stronger pull. Water on the opposite side is slightly farther away, so it feels a weaker pull. That difference matters. On the near side, the water is pulled toward the moon more strongly than the Earth itself. On the far side, the Earth is pulled more strongly than the water there, so the water is left behind. The result is two bulges of ocean water. One facing the moon. One on the opposite side. Two high tides each day. There's another way to see the same effect. The Earth doesn't sit still while the moon goes around it. Both bodies orbit a shared center of mass, a point located somewhere inside the Earth. As the Earth moves in that small circle, some of the water is flung outward slightly more than the solid Earth, while other water is pulled inward slightly more than average. Different explanations, same outcome. The tides, and the reason there are two of them, finally made sense. And once gravity was understood this way, many other puzzles cleared up. Why is the Earth round? Because gravity pulls matter inward from all directions. And why isn't it perfectly round? Because the Earth is spinning. That rotation causes the outer parts to bulge slightly outward until gravity and motion reach a balance. The same reasoning explains why the Sun is round. Why the Moon is round. Why large objects in space naturally shape themselves into spheres. As science progressed and measurements became more precise, Newton's law faced tougher and tougher tests. One of the first serious challenges came from an unexpected place. The moons of Jupiter. By carefully tracking their motion over long periods of time, astronomers could calculate exactly where each moon should be based on Newton's equations. And that's when something strange appeared. Sometimes the moons arrived 8 minutes earlier than predicted. Other times, 8 minutes later. 8 minutes. That's not a tiny error. That's enormous. Something was clearly wrong. But then a pattern emerged. The moons appeared ahead of schedule when Jupiter was closer to Earth. And behind schedule when Jupiter was farther away. A very peculiar coincidence. Something fundamental was being missed. An astronomer named Rømer trusted Newton's law of gravitation enough to look elsewhere for the mistake. And he arrived at a bold conclusion. Light doesn't travel instantly. When we observe Jupiter's moons, we aren't seeing where they are right now. We're seeing where they were a short time ago, the time it took their light to reach Earth. When Jupiter is closer, the light has a shorter distance to travel, so the moons appear on time. When Jupiter is farther away, the light takes longer to arrive, and the moons appear late. Once Rømer corrected the observations for this delay, everything fell back into place. By measuring how early or late the moons appeared, he was able to calculate something extraordinary. The speed of light. This was the first clear proof that light propagates at a finite speed. Pause and appreciate what just happened. The speed of light wasn't discovered by chasing light itself. It was uncovered by trusting a completely different law, gravity. When the data didn't match expectations, Rømer didn't discard Newton's theory. Instead, he asked a deeper question. What if the signal itself takes time to reach us? And that insight changed everything. This is why this moment matters. When a law of nature is truly correct, it becomes a tool for discovering new laws. Confidence in one truth can expose another hidden layer of reality. Without the law of gravitation, it would have taken far longer to uncover the speed of light, because we wouldn't have known what Jupiter's moons were supposed to do in the first place. That moment marked the start of an avalanche. Each discovery became a tool for uncovering the next one. And that chain reaction has been rolling forward for nearly 400 years, unstoppable, accelerating, still in motion today. But once the speed of light was known, once it was actually measured, something deeply unsettling emerged. Light always travels at the same speed. Always. It doesn't matter who measures it. It doesn't matter how fast the observer is moving. Let's make this concrete. You're standing still. You turn on a flashlight and measure the speed of the beam leaving it. 299,792,458 meters per second. No surprises. Now imagine stepping onto a train, an absurdly fast one, moving at half the speed of light. You shine the flashlight forward, in the same direction the train is moving. Common sense screams that the light should be going faster now. After all, if you throw a ball forward from a moving train, the ball's speed adds to the train's speed. But light refuses to play by those rules. You measure it again. 299,792,458 meters per second. Exactly the same. You assume something must be wrong. So you push the train even faster, 90% of the speed of light. You shine the flashlight forward again. You measure it. Still the same number. No matter how hard you try, the result doesn't change. And by now, you're getting frustrated. You push the train even harder. 99.9999% of the speed of light. You shine the flashlight. You measure the beam. Same result. The speed doesn't add. It doesn't stack on top of your motion. No matter how fast you're moving, light always leaves you at exactly the same speed. This should shatter your intuition. Because that's not how motion works in everyday life. In the real world, speeds combine. If a train moves at 50 miles per hour and you walk forward at 3, you're moving at 53 miles per hour relative to the ground. Light refuses to behave that way. No matter how fast you go, light always moves away from you at the same speed. Why? Einstein saw the only possible explanation, and it was radical. Space and time aren't rigid. They aren't fixed backgrounds where events unfold. They're elastic. They stretch and distort in precisely the right way to protect the speed of light. As you move faster, time slows down for you. Your clock genuinely ticks more slowly. At the same time, distances shrink in the direction you're moving. Space itself compresses. These aren't illusions. They aren't tricks of measurement or perception. Time really does slow. Space really does contract. And they change by exactly the amount required so that every observer, no matter how fast they're moving, measures the same speed of light. Let me say that again. The universe itself bends, stretches, and warps time and space to make sure light always moves at the same speed for every observer. The speed of light isn't just a number. It's a fundamental feature of reality. A structural constant built into the fabric of space-time. Space and time are arranged in such a way that no matter who measures it, light's speed is always identical. Now here's where it gets even stranger. Try to accelerate any object toward the speed of light, and something very unusual happens. The closer you get, the harder it becomes to go faster. Not because you're out of fuel. Not because your engine isn't powerful enough. The object itself resists. Its inertia increases with speed. Physicists call this relativistic mass increase. As you accelerate, pushing you faster becomes exponentially harder. The closer you get to the speed of light, the more your mass grows. Approaching infinity. To actually reach light speed, you'd need infinite energy. Impossible. So nothing with mass can ever reach light speed. Not due to arbitrary rules, not because of technology, but because of the very structure of spacetime itself. Light, on the other hand, behaves differently. Photons have no mass. Zero. They are allowed to move at light speed, and in fact, they must. It's the only speed they can have. Anything with mass can approach light speed, 99.9999% of it even, but it can never fully reach it. The universe simply won't allow it. And now you might ask, why? Why is the universe structured this way? Why impose a cosmic speed limit at all? Brace yourself. The answer isn't what you expect, and it might frustrate you. Here's the thing, there isn't a deeper why. The speed of light isn't some arbitrary speed limit the universe decided to impose. It's a natural consequence of how the universe is built. Space and time aren't separate entities. They're intertwined, forming what we call space-time. And space-time has a shape, a geometry, a structure. Within that structure exists a built-in conversion factor between space and time. That factor is the speed of light. It's not that light itself is special. It's that spacetime has a maximum speed at which cause and effect can propagate. Light happens to travel at that speed because it has no mass. But the speed limit itself is a property of spacetime, not of light. Even if photons didn't exist, this universal speed limit would still remain. It is a feature of reality itself. Here's another way to picture it. In daily life, we think of space and time as separate. You move through space. Time ticks forward. They seem independent. But in reality, you are always moving through spacetime at a constant rate. Always. The motion is just divided between space and time. If you are sitting still, all your motion is through time, you're moving into the future at your maximum rate, 1 second per second. But here's the twist. Once you start moving through space, something fascinating happens. Some of your motion that was going through time now gets diverted into space. You're moving through both space and time, and that means you move through time more slowly. The faster you move through space, the slower time passes for you. And there's a hard limit. If you could somehow move through space at the speed of light, you would have no motion left for time at all. Time would stop. This is why light doesn't experience time. From a photon's point of view, it is emitted and absorbed in a single instant. For light, the universe is frozen. You cannot go faster than light because you can't move through less than zero time. That's the ultimate wall. The absolute limit. And the amazing part? This isn't just theory. It has been tested again and again. Particles in accelerators reach 99.9999% the speed of light. The closer they get, the harder it becomes to push them faster, exactly as relativity predicts. GPS satellites experience it every day. They're moving quickly, and they're farther from Earth's gravity, so time ticks differently for them than for us on the surface. If we didn't correct for this, GPS positions would be off by miles in a single day. Even muons, particles created in the upper atmosphere by cosmic rays, show it clearly. On paper, their lifetimes are too short for them to reach the ground. But moving near light speed, time slows down for them. From their perspective, they survive long enough to hit Earth. From ours, their lifetimes stretch because of their speed. Either way, more muons reach the surface than classical physics predicts. This isn't speculation. It's measured. The speed of light as a cosmic limit has been tested just as rigorously as anything in physics. So let's pull it all together. Why is the speed of light the ultimate limit? Because spacetime itself is structured with a maximum pace for cause and effect. That maximum? The speed of light. It's not that light is special. It's that spacetime has a built-in conversion between space and time. Going faster would mean moving backward through time, and that's impossible. Negative time doesn't exist. You can't undo cause and effect. The speed of light is the speed at which now travels through the universe. It's the speed at which information moves. It's the speed at which forces act. It's the ultimate rate of change. And this incredible journey started centuries ago. Newton watched the moon and figured out gravity. Rømer observed Jupiter's moons and measured the speed of light. Einstein realized light speed is constant and built relativity from that foundation. Thousands of experiments followed, each confirming and expanding on these insights. Each discovery opened the door to the next. Each answer revealed new questions. This is how science works, an avalanche of discovery that's been rolling for over 400 years. And we're still riding it, moving forward at breathtaking speed. The speed of light isn't just a number. It's the key. It's what unlocks the secrets of space and time. It reveals a universe far stranger and more beautiful than we could have imagined. And the most amazing part? We can understand it. We can measure it, test it, and use it to predict reality. That's the true beauty of physics. Not comfort. Not simplicity. Truth.